Alright, welcome to another AQA A-level chemistry video. Today I'm going to be doing a video on examples of synthetic routes. So in the last video, I did a video on organic synthesis and kind of going why you need to do it, or why you need to plan out organic synthesis, why it's important for reactions, what type of why. More importantly, I asked if you ever get an exam question, what are the type of things that they'll be looking at in terms of organic synthesis. And now, when we talked about in the video, we talked about steps, percentage yield, how to improve our synthesis by reducing the amount of if we reduce the amount of steps in our process, we will reduce waste products. That would increase our atom economy, increase our percentage yield. We also look carefully about the effects of the environment, the type of solvent we use, managing safety, and these are all things that can come up in your these are all things that could come up in your exam when it asks you about how to make this, how could, for example, the reason why I did that last video was about if they ask a question about, and you know the question I'm talking about when they say how could the student improve his practical. That's what the last video was when I want to talk about organic synthesis. I'll leave a link in the description to that video. But that last video was just most about giving you the points that you need to ask, the basic points at least, for how could you improve your experiment. Now here I've just got an example of synthetic routes. This is more about questions that you need to do to actually answer the question regarding the mechanisms. So this isn't about like how can I say, application. This is just straight content here. What I'm giving you. So different routes. So people might look at, like for example, what I'm going to go through here, like for example, a methyl benzene, and how to get from methyl benzene to aromatic esters. Now I make this video because from what you know mostly from chemistry is you've been taught all the time in chemistry that how to go from one reaction to another. So go from one reaction to here. But never, and if the reaction's ever had more than one step, they usually give it to you. Now here's an example of a reaction that has more than one step, and you have to know the steps of how to get from, for example, a methyl benzene to an aromatic ester. Now sometimes in when you're answering these questions, they might give you the opportunity to see, those questions goes from step 1 to step 6. Now for some of these ones, you may have to just know by yourself how to answer them, how to do the multiple steps to get, for example, from a methyl benzene to an aromatic ester. I'm going to do 4 examples. 1, 2, 3 examples. Yeah, 3 examples here of how to get from one reactant to a product from multiple steps. And yeah, that's it really. I've kind of talked too much, and I'm going to go straight into the video now. So yeah, the first one is methyl benzene. So how can we produce an aromatic ester from methyl benzene? So the overall reaction, so we must consider the overall reaction as shown above. An ester group must be added to the side chain of the benzene molecule. Now it's not as simple as just getting the ester just to bond to getting a carboxylic acid straight to just bond here. This is just a methyl ester. We need to change this so that we're able to form the ester bond. And so the first step is that we need to substitute a hydrogen for a chlorine atom, and this introduces a carbon chloro group. So the conditions for converting the methyl group here to a methyl chloro group is we would need Cl2 and UV light. Now the reason is we need to create a nucleophilic group here. We need to get some sort of nucleophile, because we need to once we form this here, we can then do a nucleophilic substitution, and we can substitute the chlorine for a hydroxyl group. Now all of these steps, as I said before, there's 3 steps to this type of reaction here. For this particular one, all we're trying to do is we're trying to get from here to here. Now, if we want to get from here to here, we need to change this a bit so that overall we can prepare ourselves to form to allow the ester bond to form. This by itself, you can't just get a carboxylic acid. There's no hydroxyl group there. We know if we want to form an ester group, we need a carboxylic acid and an alcohol. Now we need to get an alcohol group. That means we know here we're going to get some sort of carboxyl group along the way. Along the way, at some point of this reaction, we know we're going to get some sort of carboxyl group here. Now, if that's the case, we need an alcohol group. So we need to change this group here, the benzene part. Don't worry about that. The benzene is like an R group. Don't worry about that. But we need to change this methyl group here into an alcohol. Now, the first step we're going to do that, we need this to be nucleophilic. CH3 is not nucleophilic. This here is not. This is not in any way nucleophilic. Very non-polar bonds at all. So how are we going to get a polar group bond? So now what we'd have to do is we'd have to break one of these, remove one of these hydrogens, and now get this. What we can do now is we can introduce something that's very polar, a polar compound, and that's chlorine, right? Chlorine is very electronegative, and this is now a polar bond. So if we're able to get to here, we now have a polar bond. And once we get to this part here, we can do a nucleophilic substitution with the chlorine group to get a hydroxyl group. Once we get that, we can then undergo the nucleophilic addition and elimination reaction necessary to form this ester bond here. So this first step that I was talking about is just going from carbon hydrogen to carbon chlorine. But how are we going to do that? So that's what I'm saying. In our first step, we would substitute a hydrogen for a chlorine atom, and this introduces a carbon chloride bond. Now, the actual reaction to do this, if you know Cl2 and UV light, if you know already, that would be a free radical substitution. So if you know about the propagation, initiation, propagation, and termination, right, of that, but we're not necessarily going to the whole point of ozone depletion, but what we're trying to do here is that we're trying to get UV light to separate this chloro bond here in Cl2. So we get this here, and that will undergo a free radical substitution with the hydrogen, and that would remove the hydrogen here. Sorry. Now you don't need to know about this, how to do the mechanism of this step. All you need to know is the overall steps to get to this step. Now in the exam, they'll say the reason why I'm saying these things is because in the exam they'll ask you about, they'll ask you questions saying outline the steps to get from, for example, methyl benzene to an aromatic ester. So you don't need to worry about the mechanism. Don't worry about that at all. And if it is a mechanism, it'll be a very easy mechanism that I told you before about, like, for example, nucleophilic addition and elimination. And that'll be like a part B to the question. The part A to the question, it says outline the steps that you need to take to get from methyl benzene to an aromatic ester. Now, and if you're struggling to remember how to do that, that's why I'm telling you the information here, and to help you make you understand what's actually going on here. We're trying to form that carbon chloride bond here. In order to do that, we're going to need to get this here. We need to introduce a chlorine group here. It has to be a radical chlorine because this is not a polar bond. We're not going to do nucleophilic substitution here. That's quite a strong bond. Radicals are very reactive enough to break this carbon hydrogen bond and form a carbon chlorine. That's why it has to be free radical substitution here, because this is not a nucleophile. This is not electronegative. The bond here is in the middle. It's very stable. So the electrons in the bond are in the middle here. It's very stable. There's no pulling factor from the hydrogen because that's not very electronegative. But a radical is very, very reactive, and so that would definitely displace the hydrogen, and you would now get a carbon chlorine group here. Good. That's not. I know I've kind of gone a bit too over the top with explaining that point, but that is the reason why we do that. And obviously, you need UV light to obviously separate that for the initiation there. So now we've got this. That was the first step for this particular reaction here. Now the second step is now, as I said before, the second step is now we substitute the chlorine atom for a hydroxyl group. We now have the polar atom here, the nucleophilic group here. So now we can substitute the chlorine atom for a hydroxyl group, and the reaction is carried out under reflux, and this is a substitution reaction. So this is just now a very simple nucleophilic substitution here. We introduce some sort of sodium hydroxide, a strong base, right? So once we do this reaction under reflux, and it's just a simple nucleophilic substitution. The third step now is now we have an alcohol group here now. Now we have the alcohol group, and now we can react to that alcohol. If you want to form an ester, we would now, lastly, we'd react the alcohol group of a carboxylic acid to form an ester group. The conditions are a strong acid catalyst under reflux. And obviously that would just be a nucleophilic addition elimination reaction. I'm not going to go through that right now, but hopefully that made sense. So the condition, let's just kind of summarize. Let's go. Sorry, I need to get in a bit of a better position here. Let's summarize the conditions. For all steps of this synthesis. Right, so steps of synthesis. Our first step here, so step 1, would be adding a carbo. We need to add a carbon-chlorine bond. And to do this, we would need CO2 and UV light. Step 2, we would need, step 2 is a substitution reaction, or to be more specific, nucleophilic substitution. So that we're substituting here our chlorine group for a hydroxyl group. Oh, sorry. And we'd need a, so we would need some sort of sodium hydroxide, probably strong base. That strongly associates hydroxide ions, and this was done under reflux. And then step 3, we would form an ester bond. And we would need carboxylic acid, a H plus catalyst, and is done under reflux. So carboxylic acid, a strong acid catalyst, when I mean H plus, everyone knows that acids donate H plus, so that's why I put H plus catalyst here, and it's done under reflux. Good. Okay, second part now. So benzene. So that's one reaction. Now that's just one reaction. Now you can apply that mindset to other examples. Obviously, you're not going to get specifically this reaction here. We might get specifically this type of reaction here, but just having an idea of how we get from here to from one step to the next step to the other step. So let's go to the next one here. So how to get from benzene to an aromatic amide. Think about what we have. Think about what's in your products and what's in your reactants. Now, if I want to get to an aromatic amide, we know that an amide includes this. Like, remember, when you think about amides, I always think about proteins because that's the most obvious amide that I know. Remember, in proteins, or in a polypeptide bond or peptide bond, as biologists call it, is that. Now, how am I going to get from here to here? So I know I can get to this here. I would need an amine and a carboxylic acid, right? Those are two things that you're going to get here. It's an amine reaction with a carboxylic acid. So how am I going to get that? Well, first I'm going to think to myself, I can see here they want me to get to this type of, they want me to get to here. So the amines on the benzene. So I'm thinking to myself, how am I going to get an amine on the benzene when amine, the amine that we know of, right? As if you watch my previous video when I talked about reactions with benzenes, I'll leave a link in the description to that video as well. Amine is very nucleophilic. Amine is very nucleophilic. Benzene is very nucleophilic. Benzene is even, sorry, amine is nucleophilic, but benzene is extremely nucleophilic. So that's these two are gonna repel each other. This is too electron dense. Benzene is too electron dense, so it's gonna just repel amine as it is. So how am I gonna get? Now we don't need necessarily the amine as in, you know what I mean when I say an amine group, obviously NH2, but people get what I mean. That would just break off. One of the hydrogens will just get released. But that's not what I mean. But how am I gonna get an NH2 group here in order to do to form an amide bond? Well, we don't need to form. What we can do is that we can form a nitro group. What we do know is that we can get a nitro group on here, which is NO2. Remember that, and that's via a nitration reaction, which you should know about a nitration reaction, as I said in that video, and then we can reduce the nitro group into an amine group. And once we have an amine group, then we can do a nucleophilic addition elimination reaction with a carboxyl group, with a carboxylic acid, to now form the amide. And that's how I would go through. That's how I'd go through that, right? Now, this only applies if you understand different reactions that benzene can do. But hopefully you can understand that's the mindset that I would go through if I ever saw a question like that. And make sure to highlight, when you're answering these questions, make sure to highlight all the reagents that you would use. They'd give you like a 6-mark question where they'd say outline how to go from so and so. I know, say 3 bullet points underneath that question, or say there's something along the lines of name every reagent that you have. Name any of the let's say maybe name all any of the intermediates. Something else along those lines as well. Also, they'll probably say name the type of reaction. So if it's a nucleophilic addition, elimination, a nucleophilic addition, a nucleophilic substitution reaction, electrophilic substitution, whatever it is, they might say ask that. So you won't get the maximum amount of marks if you don't answer every bullet point. So what I'd suggest is that people bring a highlighter into the exam. I know teachers say this all the time to go and do that, but it's useful for things like this where they ask you to where the question wants you to answer every aspect of the question. You say, or do what I personally prefer doing if I haven't got a highlight to me, and what I've always done is that if a question tells me to do this, so on and so on, I put like a checklist, a little box next to it, and as I'm answering my question, I can go back and I say to myself, did I answer this part of the question where they said to name and outline every part of my step? Yes. Did I mention all the reagents? No. So I have to go back on that. Did I mention this last part here about was it to say reagents again? What was the last part I said? But did I mention this last part here about if maybe they asked me to do a mechanism? Did I ask to do that? Yes, I did that part, right? And say, okay, cool. The only part I haven't done now is this, and this prevents you from answering, going back and marking your paper and saying to yourself, oh, I know how to answer that question, but I forgot to answer it because I didn't read the question fully. Now, putting bullet points next to your, or little boxes next to it, makes you go back and say, did I answer every single part of the question? No, I missed out on this part here. I can go back on it. And you should do this. You should do this as you're going through the question. But in case you forgot at the end, you can say you can go back and look at the end. And that's what I would personally do. That's what I did for my exams. But you know, go about your own way, and hopefully it helps you out. Anyway, and that's enough talking to me. So going from benzene to an aromatic amide. So how are we going to obtain an aromatic amide starting from a benzene molecule? So overall reaction, right? So first we consider the overall reaction as shown above, which is that. Now first step, so in the first step, we nitrate the benzene ring, and this introduces an NO2 group as shown below. The conditions for this are we would need concentrated HNO3. Sorry, those conditions, sorry, the conditions for the reaction. So reagents and conditions. So the conditions for this particular reaction, we need, if you remember from the nitration reaction, we're trying to form this NO2, we're trying to form a nitronium ion. And to create a nitronium ion, we need concentrated HNO3. This should be concentrated, oh sorry. I forgot to mention that, and that is important. You have to say concentrated, because you will lose a mark if you don't mention the word concentrated. Concentrated nitric acid, concentrated sulfuric acid catalyst, and 50 degrees Celsius. Now, the 50 degrees Celsius, if I'm being honest, from my experience, they never really emphasize on the temperature. If they specify the temperature, fine, but it's not like you won't. This one you don't have to worry about the least. The concentrated nitric acid and the concentrated sulfuric acid are the most important. You might even get away with just saying heating it, in my opinion. But if you should always check the mark scheme to be certain. But from my experience, whenever I was doing exams, I did my exams for the past 2 years. Don't ask why, but yeah, these are the main two that they always emphasize on. So for the nitration reaction, we'd go from here to here, nitration reaction. I'm not going to go through nitration because you should know how it goes. You can go back to the previous video where I should leave a link in the description in case I forget, but I've done a video explaining how to do a nitration reaction already. Now this is, if you know how to do this, try and complete this reaction here, try and complete this equation here. Yeah, so pause the video now and try and complete this equation for a nitration, forming a nitronium ion. Alright, so I assume you've paused the video now and you tried to do that part here. So this is important as well because remember they always tell you, they might even ask you a question and say they want you to, in the 6-mark question, one of the points I was talking about before, one of the points might be write an equation to emphasize one of the reactions that's happening, or one of the side reactions that's happening. So this is one of the things that they may ask you to do in your 6-marker. So remember to look back at during your, as I said before, if you've got bullet points. If you've got bullet points here, make sure to say, did I say the reagents? Did I say did I complete they asked me to write the equation. Did I do that? I haven't done that yet. Have I done the mechanism? Yeah, I've done the mechanism. Okay, fine. Okay, so I need to make sure I go back and write the equation out. So that's why I say that could be one of the things that they ask you. But this is not going to be too much of a problem. So NO2 plus 2HSO4 minus plus H3O plus. Now I said that there is another version of this, and it is on the mark scheme. I did it in that video where I showed you how to make the nitronium ion, but this is one of the correct answers that you could give, and this is perfectly fine. Yeah, I'm not gonna go dwell too much on that. Most importantly, you show that you form the nitronium ion. Now the second step is that we need to reduce. We now have this nitro group here, but we don't need the nitro group. That's not what's important to us right now. What's more important to us right now is that does it have positive here, positively charged. That's what I say. That shouldn't be two. That should be it's NO2. When it's bonded to the benzene, it's NO2. But remember that this is like this, but because it's positive and negative, it cancels out. It actually looks like more like this. Yeah, so that's why it cancels. In reality, yes, it's like that. But in case you get confused, that and that are the same thing. You don't need to draw it out like this. I just did it out like that, just for the sake of showing you like that. But this is more than fine as long as you show this when it's as an ion, and when it's bonded to the benzene is NO2. But that's fine. Now the second step, now we're trying to get from this to an NH2. We need the NH2. We need to reduce this nitrile to a nitrated benzene in order for it to form to react to carboxylic acid to form an amide. So we need to reduce the nitrated benzene, we would need tin and HCl, and this forms a protonated product as shown below. And you'd need the first step, which is to neutralize the protonated amine. We must add base so to obtain the aminobenzene as shown. So step 2 and step 3 kind of coincide together, where if you want to go from a nitrated benzene to an amine, you would need to obviously reduce it with tin and HCl. But in order to neutralize the protonated amine, we then add a base to obtain this aminobenzene here as shown above, and that's it. Those are 2 things. So tin and HCl and a base such as sodium hydroxide to neutralize the protonated amine. and that's it. And fourth step, now we have this here. Now we have this from the second and third step. Now we have this here. Now the last step is now we're trying to form the amide bond. We then carry out a condensation reaction to create the amide bond using an acyl chloride. So it could be an acyl chloride. What was I going to put in here? Sorry, I said carboxylic acid the entire time. It would be an acyl chloride. Sorry, my bad. I forgot. I actually kept on saying acyl chloride. It can be a it'll be an, I mean, it could be a carboxylic acid derivative such as an acyl chloride. It doesn't have to be necessarily. It could be also an acid anhydride, but anything with the carbonyl bond. So carboxylic acid, acyl chloride, or a acid anhydride. Those all can form an those can all form a an amide bond, as said before in previous videos anyway. So I want you to try and do. I'll allow you to represent it like this. I want you to do a nucleophilic addition elimination reaction just to kind of test your ability on this. And I'll show the acyl chloride that we had, which was Now I want you to go from here to form your amide bond here. And you don't have to represent the benzene. You can just relieve the benzene as R. You can represent benzene as R. I want you to form an amide bond here and do the mechanism for that. You know it's a nucleophilic addition elimination reaction. It's very easy to see that. Why? Because we have a nucleophile. Look, going from here, we're trying to form this, right? A nucleophile is being added. If a nucleophile is being added, and then there's an elimination reaction, removing a. What are we removing now? We're removing a chlorine group. So it's nucleophilic addition, elimination. So do that reaction now. I'll pause the video now and try and do that. Alright, so I'm going to assume that you've already tried to do that. I'm going to create a bit more space for myself here. We'll then form this intermediate here. I'll allow you to do this. Even if you left it in a skeletal formula, it's fine, but I'm just going to do it like this just for the sake of making it clear what's going where. Could I have left it alone? I could have done it as a skeletal group anyway, really, but doesn't matter. Doesn't matter at all. That forms there. If that's going back, then that's to be that, and that is that. And there we go. And then we have HCl as it, but that is the exact same thing as. You can leave it in the skeletal formula if you want, but I just prefer doing it in the structural formula. But that is the same thing as the R group, which is the benzene. I guess people really want the benzene, but that is the same thing as what we have in our. And that is all. And now that's it. We now form our aromatic amide or phenylamide. This would be a phenylamide, but that's how you done it there. So if I'm going to summarize step 1, I'm not going to go through the whole deal of writing everything down. Step 1, nitrate the benzene. and you'd need concentrated HNO3, concentrated H2SO4 catalyst, and then you'd need, you could say heat, or I guess technically 50 degrees Celsius, but you could probably get away with heat. Step 2, we then reduce the nitro group to a NH2, so reduce nitro to amine. We'll call that nitrobenzene. Convert the nitrobenzene, I should say. So reduce nitrobenzene to phenylamine. And that requires tin, HCl, and sodium hydroxide base. And then the third thing to do here is create an amide bond. And then we need now it could be an acyl chloride, so I'll say it could be a carboxylic acid or carboxylic acid derivative. So carboxylic acid / derivative. There's not enough space here. I thought there's an arrow here so it doesn't confuse people. An acid catalyst, we need an acid catalyst. And we need to do this under reflux. Last one. Again, if I'm going too slow for you, you can just skip to the part where it's necessary. But I'll try and go this. Now everyone understands how I structure my answers. I'm just going through every little bit of detail so that people kind of go from understand my methodology to go through these questions, rather than just going through and say this is this and this and this, because you're not always going to get this example. It's about understanding how, if I ever got a question that's not ethene to propyl amine, which is the next one I'm going to do here, how does I go about doing the steps. It's just about thinking about how to go from here to here, you know, that, and where they go. And now I'm going to go to the next one here. So how can we form a propyl amine molecule from ethene, right? So overall reaction is this. We need to consider the overall reaction as shown below. So we have an ethene and we have a propyl amine, right? So ethene is 2 carbons, propyl amine is 3 carbons. So it means you have, at some point, we would have added the carbon, right? The way I see it is that we need to break this double bond here first of all, because that's an alkane and this is an alkene. So it'd probably be some sort of addition reaction. Once if I can do it, I can I could probably do an electrophilic addition with I probably have something to do with HCl. Yeah, or hydrogen bromide. Hydrogen bromide could work. Yes, I don't want to have bromine Br. I don't want to use bromine water because then I'll get a random Br2 here. So I can use bromine water. I can use HCl or hydrogen. It has to have hydrogen in it. So let's say hydrogen bromide or hydrogen chloride to get just to get a hydrogen and a some sort of nucleophilic group here. So it's still got some sort of like this. But now it's like this now in our step. This is how I plan out, right? This is how I plan out. Now I don't remember what I wrote down for here. I'm just kind of going as I go along. But that's how I think about it. So now I have that and I have this. So now I have that, but I need to add a carbon and a nitrogen. How do I do that? I can do that in one step. I can do a nucleophilic substitution reaction because with a cyanide group. The cyanide group is nucleophilic. This what's it called again? This will probably be a halide or halogen group here. I can just do a simple nucleophilic substitution with this, and now I have a C and an N. And then when I get to that there, I'll go form this here CH2, CH2, and then I can reduce this cyanide group here to form. So I can reduce the nitrile. This is now a nitrile group now. I can reduce because I have this is a nitrile. I can reduce this nitrile to form a I don't remember what I used to reduce, but I can reduce the nitrile to form an amine, essentially. Yes. And then once we have that, I now have a propyl amine, because this would be CH2 here, CH2, CH2, and then an amine group here. So that's how I'd go about it. Let's see how it's meant to be done at least. So the alkene undergoes an addition reaction to gain a... Does this actually go through? Yes, it is. Yes, okay, yeah, it is how I thought it was going to be. So the alkene undergoes an addition reaction to gain a chlorine and a hydrogen atom across the double bond, and this requires a HCl. So yeah, they're using HCl here. I mean, hydrogen bromide, hydrogen chloride. Again, in the mark scheme, you could use either or. They wouldn't say you can only use hydrogen chloride. You could use hydrogen bromide. The same effect would be. So don't worry about that. So I'd undergo a nucleophilic, so addition, an electrophilic addition. Now I want you to try and do the electrophilic addition if you struggle to do it, but so if you need help doing it, but pause the video now and try and do it. It should take you very quickly. You should be able to do this, quickly by now. So how do you go about it? I assume you've unpaused the video now and you've tried to do it by yourself, but you should know from now to get from here to here, partially positive, partially negative. There's no overall, the carbocation can be on any one of these because they're both, it's an ethene, so there's no side group, so it'll be exactly the same on either side anyway. You should be able to do this in seconds as I've done it right now. So I use hydrogen bromide for some reason, that's really weird. Same thing anyway with the chlorine group. Yeah, I forgot they're not using hydrogen bromide, they're using hydrogen chloride, but it's the same thing anyway. Same thing anyway. And hopefully that made that should make sense by now if you're doing year 2 now. And now the second step, now we substitute the chlorine atom for a cyanide group, and that would come from potassium cyanide. I already explained why potassium cyanide in a previous video. I explained why potassium cyanide is better than is better than hydrogen cyanide. Potassium is it's a bigger atom. So it has a weaker attraction to the cyanide group here, and weaker. The nucleus is further away from the bond, so it's a weaker attraction, and therefore it's more likely to dissociate cyanide ions. That's what we want to do. We want to get this cyanide group here. We don't care about the potassium. The potassium is a spectator ion. So by having potassium cyanide would dissociate, would more strongly dissociate cyanide ions compared to hydrogen cyanide, and that's why we'd use that. And if you went a bit further on, the dissociation or acid dissociation is what they would use. Constant is higher with potassium cyanide. Now if you haven't done acids and bases, the thing I talked about, the acid dissociation, won't make any sense to you. But if you know about acid dissociation constants, or dissociation constants in general, having a higher dissociation constant means it's more likely to get dissociated. So potassium cyanide is the reagent that we'd use. So we'd substitute. It's now just a simple nucleophilic substitution with a cyanide group. Now the conditions are ethanolic and they'll be done under reflux. That's what you need. You need to have ethanolic conditions. I don't know why the water is, but for some reason Seneca said you can have water. So I assume that means aqueous. I think that means, yeah, aqueous. That's probably what they meant by water. Aqueous conditions. ethanolyc conditions under reflux. And then yeah, simple substitution. I'm not gonna go through substitution. You should know that by now. And now the third step is that, and then lastly, we now have the extra carbon, and we now have the nitrogen. Now we can reduce the cyanide group to form an amine group, and this requires a reducing agent. Now the reducing agent that we know for reducing nitrile is either LiAlH4, but the one that I prefer using and the one I suggest that you guys use is H2 for nickel or platinum catalyst. You will get the mark for saying LiAlH4, but as I explained in previous videos, if they ever ask what, the only reason why I don't say use the LiAlH4 is that if they ever ask you a question about I never have seen a question on it, but in case they ever want you to answer, I think I may have seen one question on it, but H2 and nickel catalyst is much cheaper than LiAlH4, but really you can use either or. But the one that everyone knows is H2 with a nickel or platinum catalyst, and that's fine. And that's just reducing our nitrile group into a amine. And now we finished. Now we've gone from ethene to a propylamine. That's it. Hopefully the video was helpful. If you found it was too long or it was kind of dragged on, let me know in the comments. I just want to make these videos as more useful to you as possible. And that's it.